It can land on heads or tails.
All right. If I flip a coin one time, I can either get a head or I can get a tail. And that represents the sample space for flipping a coin one time. It's ridiculously easy, right? It's hard to mess that up. You write it down in a list. It's small, so it's easy to come up with that answer. Okay? But what about flipping a coin two times? Take a moment to think about that. So clearly you can see if you flip a coin twice, there's actually 4 different ways that can happen. 2 heads or 2 tails, and then a head tail or tail head. And a head tail tail head are different. So take a moment to see if you can write down all the possible ways for flipping a coin 3 times. Are we confident that we've listed all of them here? Yes. Okay. Well, we might feel okay as far as confidence goes, but we weren't super organized in the way we wrote this. So what I want to do is, this is the correct list, but I want to rewrite it in a different manner. Remember, if I flipped the coin the first time, I only had a heads or a tail as a choice, right? Now, the second time, if I flip it the first time and get a head, what can happen when I flip it again? I can get a head a second time or a tail, right? Now, if I flip the coin the first time and get a tail instead, then I could still get another head or a tail on my second choice, right?
No, it's not.
It's not confusing.
Now, of course, these represent the first flip. These would be the second flip. Now, if I did it a third flip, I could have a head on the first flip, a head on the second flip, and then I could get a head or a tail again. Now, what if I had a head the first time and then a tail the second time? I could still get another head or a tail. And most of you can see quickly that I can have a head or a tail choice for each of those. And as you can tell, what this does is it makes us the same list that we just had, but it's a little bit more organized. It's a little bit more predictable as far as trying to write a list out.
Well, then how did you get all them though? Did you just go from the side?
So there's 2 possible outcomes here. How many possible outcomes if I flip a coin twice? 4. And you've got that on that tree diagram. And how many possible if I do it 3 times? 8 times. So these are our possible outcomes. So these are all denominators. All right, now we can look here. The probability of me getting a head if I flip a coin 1 time was what? There's only one way I could get a head, and there was only 2 ways possible. So it was 1 out of 2. And I know you guys know that that's 1 out of 2. It's 50%, because this is a super easy example. But you have to establish the pattern. Now, the probability of me getting a tail is what? It's the same thing. There was only 1 possible tail that happened out of 2 possible outcomes. So 1 out of 2 tells me my definition. All right? Now, obviously, these don't make sense. Here and here. Now, let's look here. The probability of me getting only heads. If I flip a coin twice, what was the probability of me getting only heads? It only happened 1 time. Remember, I had a HH? 1 time. But how many possible ways were there? 4. So it was 1 out of 4. Which is 25%. And what about for probability of tails? The TT, only tails? Once again, it was only 1 out of 4. What about a head and a tail? How many different times did that happen? Remember, I had a HT and I had a TH. So a HT and a TH, I can just count. That's 2 out of 4. Ended up being 50%. Right? Now, how does that change when I flip it 3 times?
It goes 1 8, 1 8, and 6.
All right. HHH. If I flip a coin 3 times to get only heads, I have HHH. That only happened once, right? But there were 8 ways that could happen? Yes, ma'am. Now, if I were going to do this, what things could happen with roll 1? I could get what kind of numbers? 1, 2, 3, 4, 5, and a 6, right? And now for roll 2, if I were going to add them up, if the first one was a 1, the second one could be a 1, or a 2, or a 3, or a 4, 5, or a 6, right? And what's going to happen to this? It's going to get very crowded very quick. This is not a good way of doing it. What we would do is, because we recognize that a tree diagram is going to get very ugly very quick, is we don't want to go about doing it that way. Instead, we would be much better off creating a table. Okay? A table would work out really well for us in this situation, because we're only talking about 2 events. Okay? If you have 2 events, a table works out well because you got a length and a width, right? So if my first dice was a 1, 2, 3, 4, a 5, or a 6, then the second dice could also be a 1, 2, 3, 4, 5, and a 6. And it would be very easy, hopefully, to establish all of the sums by creating a table. All right. So what we can do at this point is just kind of create a little table, and you could tell me the sum, because remember, I'm supposed to add the 2 together. So if I had a 1 plus a 1, that'd give me a 2, right? And if my first dice was a 1, excuse me, my first dice was a 1 and my second dice was a 2, my sum would be a 3. And if the first dice was a 1 and the second dice was a 3, and if the first dice was a 1 and a 4, and you can see the pattern. All I'm doing is adding those up, right? Now this column represents the first dice is a 2, the second dice was a 1, so the sum of 2 plus 1 is 3, and 2 plus 2 is 4, and 2 plus 3 is 5, 6, 7, 8, right? So go ahead and fill in the rest of that table. Go ahead and fill in the rest of that table. So you recognize that 6 by 6, you recognize there's 36 possible outcomes, right? And the great thing about this is you've written down every single one of them here. So it's easy when you see the sample space to answer probability questions. Let's look at the probability of getting an 8. There are 1, 2, 3, 4, 5 different ways that I could add up to get an 8. So that's 5 out of 36. Which is a fraction. What's that decimal? 0.138. So about 0.14, about 14%, right? Yeah. What about the probability of me getting bigger than a 10? Now 10s, do they count? No. So it has to be bigger than a 10. There are only 3 different ways that I can get something bigger than a 10. That'd be 3 out of 36, which of course reduces to 1/12, which is about 0.08, so about 8%. What about a probability of a 1? Which number, how many times can I get a 1? I cannot. It never happens. It's never in my sample space. So there are 0 opportunities for me to get a 1. So of course my answer is 0. Now, this last one's an interesting one. What about the 6 or the 9? How many times can I get a 6? 2, 3, 4, 5. There's 5 different ways for me to get a 6, right? How many ways for there to get a 9? 4. So how many ways are there total? Ooh, that should be 36, sorry. So there's 9 out of 36 ways for that to happen total, right? Which that does reduce, of course, to 1/4, which is 25%. And of course, this is true just at the store down the street. So a rack has a mix and match swimsuits. There are 3 different bottoms that I could choose from. Okay? And once again, I'm going to find out that this is tedious to draw the entire sample space. Obviously, I could have, in my decision, I chose red and orange and blue. Now, how many different tops could go with those? Okay.
4, 8.
I could have a red top, or a rose top, or a yellow top. Let's not judge my fashion here. Okay. So there are obviously 4 different choices of tops for every bottom, right? Is this going to get tedious again? It will get tedious. So I could go through, and then I could do cover-ups on top of those. Each one of those tops could have a cover-up, which should be different colors.
24 different options.
Right? So you can see that it becomes very tedious.
Okay, did you put yellow?
It's like
blue,
this.
and green?
It doesn't work
You
that
don't
way on
put
this.
red and yellow together, right on top.
Okay? It becomes very tedious, doesn't it? All right? But most of you can see right now that there's going to be 24. There's 8 different ways that this can happen.
And then 8.
And then this one's going to have another 8. And this one's going to have another 8. And it's going to be 24. The question becomes, when does the sample space become too tedious? Does it really matter that I know a red bottom, a rose top, and a yellow cover-up? Oh, that'd be horrible. It doesn't really matter, does it? Okay? What matters is the total number, and the total number is 24. So we want to get away from that, and we want to talk about how to get it there. And that's going to be 3 bottoms times 4 tops times 2. What's 3 times 4 times 2?
24.
It's 24. And that leads us to what some of you already know is called the fundamental counting principle. You guys have seen some of the new restaurants out there that have this soda machine where you can just press a button and then choose different flavors instead of having to,
Like the movie theater.
yeah, like the movie theater has it.
They can butter on popcorn.
Okay. So a new soda machine, if I were going to do this with using a sample space, I'd have to show all 8 different sodas, right? And then each of those sodas would have 5 different flavors for them. And how many is that going to be? It's going to be 40, and visually you can see it's going to be 40. But nobody wants to draw all this out every time, right? So instead, we just use the fundamental principle, which tells us 5 different flavor choices for 8 different drinks has got to be 40 total choices. And I don't have to write down and show every single example. Now you can compound that. You can take this same soda machine, put it in an ice cream shop that has 3 different flavors of ice cream, and now how many different floats could you have?
120.
Okay, now I add those 3 to this, and I get 120 different floats. Now, does that mean that this ice cream shop has 120 flavors of ice cream?
No.
No, but it means that if you were going to buy a float there, they could offer you 120 different choices without having to repeat themselves. Is that something that they would like to advertise? Probably. Think about some of your Subway commercials, all right, and stuff like that. They do like to advertise how many different choices you get. 4 numbers after that. Well, what kind of numbers could go here?
0 to 9.
0 through 9. How many digits is that?
10.
There's 10 of those, right? So there's 10 possible numbers that could go here. How many could go here? There are still 10 choices for those numbers, right? And how many for the third slot? 10, because I could have any of those numbers, 0 through 9. And then what about here? 10. Well, the fundamental counting principle says if there's 10 ways for this one and 10 ways for this one, then what do you do with all of those?
10 times 10 times 10 times 10.
And you get
10 to the 4th, which is
10,000.
10,000.
10,000.
All right? So that right there, how many letters can there be? Oh, wait, there's 3 letters and then 4 numbers.
26.
Okay, so there's 26 possible letters here.
Yeah, there's a lot.
and 26 here. Now, what kind of digits can go here? 0 through 9. So that's another 10, and another 10, another 10, another 10. And the fundamental counting principle tells you that you multiply all those together.
Oh my.
So somebody help me out.
Head math.
What does that E mean? Does it mean
Okay, this last one has a new license plate. It consists of a, what does it say? A 1 non-zero digit here, followed by 3 non-O letters, one here, here, and here, and then 4 non-repeating numbers. What kind of numbers am I going to fill in here? I'm going to have to get rid of this last one for some space.
well, okay, you can have 9, 8,
All right,
6, 5, 4,
1 non-zero digit. How many choices are there? There are 9 choices for a non-zero digit. I took the 10 normal digits, I took 0 out, so there's only 9 choices. Times, I can have 3 non-O letters. So that's 25 times 25 times 25. And then 4 non-repeating numbers. So how's that going to be? Okay, I have 10 choices for the first one, but then I can only have 9 for the second one, right?
Wait, does the non-zero still count for the ones after that?
Oh, that's a great question. As of right now, I'm looking at 10, 9, 8, 7. Now, your question was, does this non-zero number up here count for the non-repeating? Well, we'd have to decide that, wouldn't we?
Yeah, I would say no.
If we want to say, probably say no because they're separated. Let's just assume not. If they were, we would have to adjust these. So now go ahead, somebody multiply that out for us. So it ends up being a lot, right? All right.
That's a lot.